When microfluidics came into existence, a big buzzword came in the market which was called as lab on a chip. Lab on a chip is such a big buzzword that it created a sensation in the market, and the whole idea was that in the biochemical processing you do a lot of activities in a lab. A big, for example, a big biochemical activity undertaken in a pathological laboratory. So, you have valving, mixing, metering, pumping, so many activities concerning some fluids and chemicals. So, these activities if you miniaturize in the form of a small credit card type of a chip on which you perform all these operations, taking all samples in very small volumes and doing rapid work with that with a very low cost paradigm. So, that was the essential hallmark of a lab on a chip device. Now, today what we will discuss is a variant of the lab on a chip which we call as lab on a CD. So, lab on a CD, by the name itself you can understand that it is essentially a variant of the lab on a chip, where instead of the credit card type of a chip you have a CD type of a device. So, how the CD type of a device looks like? It looks like exactly the CD that you have for external data storage in a computer, except for the fact that the materials may be different. So, instead of the material that you have for the CD for external data storage in your computer, you could have a CD where the material is made of polycarbonate materials. The CD is made of polycarbonate materials. So, what you essentially try to do with a lab on a CD? See, I will get into the details, but for every lecture at the beginning I want to give you an overview that what it is about that we are talking, and then we will get into the details. So, you have a disc, and let us say again the objective is to do some medical diagnostics. So, here let us say there are certain channels which are cut in the disc. I will show later on how channels are cut in the disc. So, now for the time being imagine that there is some channel in the disc, and let us say that here there is some reagent, and then you let us say that through the central reservoir you insert a drop of blood. Now, this CD material being hydrophobic, the blood will be forming a meniscus like this, and it will not actually be driven towards the target site. Had it been hydrophilic, it would be spontaneously moving by surface tension driven flow. So, something has to drive it. So, what will drive it? You make it rotate with respect to its axis. So, if you make it rotate with respect to its axis, by centrifugal action this will be moving, but there is a critical rotational speed at which it starts moving, and then it will go to the reaction site, it will do a reaction, and then based on the result of the reaction some disease can be detected. So, this is a broad motivation why we want to study the essential science of the lab on a CD. Okay. So, now when we are studying lab on a CD, we have to keep in mind, and we have, this is very interesting, we have studied already pressure driven flow. So, pressure driven flow has certain characteristics. Now, the lab on a CD, this is also essentially a device with pressure driven flow, but the pressure gradient is created by centrifugal action. So, fundamentally it is a pressure driven flow, but by altering the rotational speed you can vary the effective pressure gradient over a large range. such a large range of pressure gradient you cannot create in a simple syringe pump control device. So, that is the unique advantage. So, if you look into this chart, a comparative study of the scaling of different types of flows, micro flows. So, if you look here, see, let us compare the pressure driven with the centrifugal. Electrokinetic we will study later on, and acoustic is not a part of this small short course, but if you see the pressure driven flow, if you recall the Hagen-Poiseuille equation, the head loss for a given flow rate is inversely proportional to the fourth power of the diameter. So, the head loss scales with 1 by L to the power 4. For the centrifugal also it is 1 by L to the power 4, because this is fundamentally pressure driven. Flow rate, see, pressure driven flow can give flow rates from nanoliter per second to liter per second, but liter per second flow rate with pressure driven flow in a microfluidic device, it is unimaginable. I mean, so this is not just a microfluidic range, but this is the general range, whereas centrifugal force you can easily vary the rotational speed to have the flow rate even less than 1 nanoliter per second, very low flow rate, to large flow rates maybe greater than hundreds of microliter per second. Materials used are almost the same, like plastics, PDMS. The pressure driven flow had certain problems that we discussed. Centrifugal force driven flow or rotational microfluidics, it has a very unique problem, that is, if you rotate the CD at a very high speed you will get a very high output, but you will get vibration of the setup at such a high speed, and that vibration can spoil many activities using the setup. So, with this little bit of comparative study, let us see that what kind of paradigm we can look for with CD based microfluidics. So, you have a motor on the top of which you have a CD, and imagine that this CD is linked with a computer system, or it is linked with a DVD player at least. So, you can have optical readouts on this also. So, that means you can integrate optics, informatics, fluidics, everything together on a single platform. See, such a unique platform where you could integrate optics, fluidics, informatics, and that makes this so special, and in fact you can store information, store data in such devices. So, how is the fluid flow controlled here? The fluid flow is controlled by rotational speeds and by design of microchannels. So, how the rotational speed can control the fluid flow? The effective formula is worked out in the slide, but for your convenience I will also work it out in the board. Let us say that you have a fluid which is filling a part of the capillary in the CD, and then we consider a small element dr in the radial direction. The radius limit is from r equal to r1 to r equal to r2. Of course, the meniscus is not flat, but just for simplicity I have drawn it like flat. It will be curved with curvature bend inside because it is a hydrophobic material. So, let us identify what are the forces which are acting on this element. So, let us say that you have pressure here P and here pressure P plus dP. If we are sitting on this fluid element, then this pressure gradient will be balanced by a force which is called as centrifugal force. So, this is P into area, this is P plus dP into area. Or if we are sitting not on this disc, we will see that there is an acceleration which is towards the center, which is called as centripetal acceleration. So, centrifugal force is an equivalent pseudo force that you feel if you sit on the rotating platform, and centripetal acceleration is an acceleration if you make an analysis on an inertial reference frame by sitting outside the rotating material. So, let us think about that inertial frame based analysis. So, resultant force is equal to mass into acceleration. So, resultant force is P into A minus P plus dP into A. What is the mass of this? A into dr into rho into acceleration is minus omega square r. Let us say this radial location is r. Okay. So, P into A, let me write it again because it is not being covered by the camera properly. So, P into A minus P plus dP into A is equal to minus A rho dr omega square r. So, you have dP dr as rho omega square r, right. Now, if you integrate this from this section 1 to section 2, r dr is r square by 2. So, it becomes rho omega square r2 square minus r1 square by 2. Okay. So, now when you have this P2 minus P1, so P2 minus P1 into A is the net driving force. And what is the resistive force? Where A is the cross sectional area of the channel. What is the resistive force? Resistive force is the surface tension force here. See, it might be confusing to you because in one of the previous chapters we were studying surface tension driven flow. Now, you might argue that just few chapters back you are talking about surface tension driven flow, now you are telling surface tension as a resistive force. See, surface tension has become a resistive force because the contact angle has changed here, it is a hydrophobic material. So, the resistive force is sigma into the perimeter, which we call as C here, because P we have already preserved for pressure. So, sigma into perimeter into cos theta. Okay. So, here the if you look into the meniscus is like this. So, this is the direction of flow, surface tension is trying to hold it like this and centrifugal force is trying to move it radially outward. So, this is the force balance, the physical force balance that you are going to have here. So, when will it start moving? The fluid will start moving when the rotational speed is just enough to make the centrifugal force overcome the surface tension force. So, that is P2 minus P1 into A is greater than equal to sigma into C cos theta, where C is the perimeter of the cross section. So, that means this is rho omega square R2 square minus R1 square by 2 is equal, this is greater than equal to into A is greater than equal to sigma C cos theta. So, from here you will get a critical omega. So, we get a critical omega, critical rotational speed at which the disc will at which the capillary will start getting filled because of the surface because of the centrifugal force driven flow. So, that frequency at which the fluid starts moving across a channel, omega critical, if we call it 2 pi f, then this f is called as burst frequency, BURST, burst frequency. So, this burst frequency is a very important design parameter, because you must know that what is the rotational speed at which you must rotate your CD to make the sample move, right. One question, by looking into the burst frequency you can see that there is no effect of viscosity in this. Can you tell why? The reason is very simple, that viscosity is there when the fluid is under motion. The burst frequency makes a calculation when the fluid just starts its motion. So, when it just starts its motion, the viscosity is not playing its role. Viscosity is playing its role when the fluid is already under motion. So, it is primarily the density of the fluid that plays the role, but viscosity does not play any role in dictating the burst frequency. So, if you are now calculating this particular effect on a practical CD type of device. So, if you go through this slide, you will see that this therefore can be designed as a smart centrifuge. So, you have an idea of a centrifuge which is a large rotating device which is there in almost all good pathological and biochemical labs. Now, here instead of a large centrifuge you can have a small disc carrying that task. So, possible applications could be biochips, nano and micro scale water power systems, diagnostic devices and other optically powered nano machines in aqueous environment. So, it is up to your imagination how you want to use these kinds of devices by simply using the rotational effect. Now, the question is, the next question, this is a very important question, that why is CD used as a microfluidic platform? That means these plastic based CDs. So, why we consider the CDs as microfluidic platforms? The answers to these depend on the specific applications. See, most of these applications are essentially biological applications. So, the CD is an excellent microfluidic platform because it is biocompatible, it is an effective substitute to standard consumables like slides, microwells, centrifuge tubes etc. used in pathology laboratories. It is versatile in handling a wide variety of samples. It has the ability to get the flow of liquids, that means by operating the device at certain rotational speed you can stop the device, by rotating it beyond the critical speed you can start rotating it. The motor requirements are very simple, the fabrication is also very economized, and it is possible to perform simultaneous and identical fluidic operations. So, it is a very simple technology and a low cost platform to do a large pathology on a small disc. So, what are the features of this? Flow rates ranging from less than 10 nanoliter per second to greater than 100 microliter per second, this I have already mentioned. The pumping is relatively insensitive to physico-chemical properties such as pH, ionic strength or chemical composition. There later on we will study another method called as electrokinetic flows, where the pumping is sensitive to physico-chemical properties like pH, ionic strength, chemical composition etc., but that has its own unique advantage, so that is why we study that. Aqueous solutions, solvents like DMSO, so DMSO is a very unique solvent like dimethyl sulfoxide. It is a chemical which is normally produced as a byproduct of paper technology, so paper production device, but later on it has been found out that it has many characteristics to be used as a drug for certain diseases. So, DMSO is a very important fluid. Surfactants, biological fluids like blood, milk, urine, these have all been pumped successfully using this device. Now, making microchannels on the CD is relatively very easy and it is easily implementable. Not only that, a whole range of functions including valving, decanting, calibration, mixing, metering, a wide range of functions can be integrated on this microfluidic platform. So, what are the important forces? Let us look into this slide very carefully. So, you have already we have discussed about the centrifugal force and the surface tension driven force, but when the disc is moving and rotating and the fluid is moving on it, there is an important force which is called as Coriolis force also. So, what is the Coriolis force? So, if you have a fluid translating with respect to a rotating platform, then it will be subjected to a sidewise force. So, if you look at this, for example, if you have the disc rotating like this and the fluid is moving in this direction, there is a sidewise force which is called as the Coriolis force. So, the Coriolis force is the force felt because of translation of something, particle, fluid, whatever, with respect to a rotating reference frame. So, here the fluid is translating with respect to the rotating reference frame and that gives rise to this kind of Coriolis force. So, this Coriolis force is very important for separation of particles because you can push them into the sidewise direction. Also, you can have a Euler force. Euler force is because of the angular acceleration. So, if you now vary the rotational speed of the disc, you can create an angular acceleration and that can give rise to the Euler force. In addition, you can have a viscous drag force. As I told you just a few minutes back that viscous drag force is not important for burst frequency calculation, but once the fluid is moving on the CD, there will be a viscous force. So, you can see here that you have centrifugal force, Coriolis force, Euler force, surface tension force and viscous force. So, you have so many forces which are interplaying with each other. So, this lab on a CD is a wonderful thing in science. On one side you can study very rich fluid mechanics, very interesting fluid mechanics by looking into the interplay of all these forces. On another side you can use this interplay of forces to design a device that can solve medical problems, that can that can do biomedical diagnostics. So, how is a CD made or how is a CD manufactured? This is essentially again a wonderful thing, because CD is manufactured in a method where you do not use clean rooms. So, this has been a revolution in microfluidic technology, because for a long time the clean rooms were used for making microchannels. Now, this CD manufacturing does not need a clean room. So, you can use a low cost facility with mechanical micro manufacturing to make the CD. So, I will show you how this CD is made in different layers and these layers are bonded together. So, we have a 3 layer approach or a 5 layer approach. This example is a 5 layer approach. So, this layer 1 is a top plate, it has venting holes. 2 and 4, these are not really polycarbonate discs, these are essentially pressure sensitive adhesive layers. So, these are adhesive tapes in which you can simply cut microchannels. In the middle plate it contains all the chambers, this is a polycarbonate disc, and then you have a bottom disc with alignment holes at the same positions. So, now you can bond this entire system stack together to make a single disc. So, it is just like making a burger. Of course, I mean the meat in the burger is very interesting, the CD making may not be that interesting, but I mean it is essentially as simple as that of I mean making a burger by stacking various layers. So, finally, how do you do experiments on lab on a CD? So, this is a typical experimental setup. So, you have a simple servo motor which rotates the disc, you have a camera and you have a strobe light which flashes the light at every complete revolution. So, that means a point which after one complete revolution comes back to the same point and there the light will be flashed. So, you can make one point which is actually moving to appear stationary, because the point has come back to the same location. So, this is the essential principle of a stroboscope for making a cyclically moving object appear to be slow moving or stationary. So, you have essentially a computer and CCD camera to acquire the image, a detector plus computer to obtain data and also feedback of the motor unit. So, this is a complete setup, and this lab on a CD can be used to do very interesting medical diagnostics in a resource limited platform, and that essentially is a very important component of biomicrofluidic research. So, with this we conclude this lecture. Thank you for your attention. We will come up with a different topic in the next lecture.